And I would like to thank the organizer for inviting me to give a talk here in this venue. It's great that so many people are attending online. So let me share my screen and start my talk. Okay, so I'm going to talk about computing endomorphism rings of supersingular elliptic curves. And what I'm going to talk about today is joint work with Sean Hallgren, Chris Leonardi, Travis Morrison, and Jennifer Park. So, in this talk, the new algorithm for computing endomorphism rings that I'm going to give is going to be just for supersingular elliptic curves, and the running time will be O of square root p log p squared under certain heuristics. So let me say a little bit of about how the talk is organized. So in the beginning, I'll talk a little bit about the interest in the problem, what the connections are to post-quantum cryptography. I'll talk a little bit about supersingular elliptic curves and properties of the endomorphism rings, and then I'll give the new algorithm. So that's how the talk is organized. And so, well, what is post-quantum cryptography? The goal is to develop public key cryptographic algorithms that quantum computers cannot break. So what does that mean? Well, let me tell you some bad choices. RSA is a bad choice since it can be broken if you can factor, which can be done efficiently on a quantum computer. Traditional elliptic curve cryptography is also broken by quantum computers, and so are certain very special systems that based on very restricted type lattices. So there are many lattice systems that are not broken, but some very special ones are, and an example is soliloquy. Well, and then the question becomes, well, what are the good choices? And at this point, we don't really know. And we just have to study a bunch of open problems. One is the shortest vector problem, lattices, and another one, and this is what I'm going to concentrate on today, has to do with elliptic curves, and in particular, computing isogenies between them. Okay, so how are elliptic curves used for post-quantum crypto? The new proposal relies on isogenies between elliptic curves. And just to contrast that, I want to say what traditional elliptic curve cryptography looked like. So in traditional elliptic curve cryptography, you have an elliptic curve, you fix the, you have the group law, and you assume that when I give you a, if I give you a point on the elliptic curve and I tell you it's some multiple of another point, it's hard to figure out what that multiple is. So that's the discrete log problem on the elliptic curve. And the advantage is that you get pretty small key sizes compared to something like RSA. The downside is that Shor's quantum algorithm completely breaks these cryptosystems. So that means they're not interesting for post-quantum cryptography. And that is where a new proposal comes in that was developed several years ago. I'll say something about that in a little bit. Namely, you use all elliptic curves defined over some finite field and the isogenies between them. And so here is sort of an overview of what the systems are that are currently in place. Is the first two rows, RSA and ECC, and the underlying hardness assumption, factoring, and elliptic curve discrete log. And then we sort of have one of the big lattice options for post-quantum cryptography, ring LWE. Then the one I'm going to talk about today, supersingular isogeny-based cryptography. And then just to throw in another one is again this soliloquy from before. And PIP stands for the principal ideal problem in number fields. And so for each of these, we have underlying hardness assumptions, and they're very different, and we have to figure out how hard these problems are that these systems rely on. Okay, so what kind of isogenies-based systems exist and how long have they been around? So the hash function is the one that's been around the longest. That was developed by Charles, Gorn, and Lauder in 2006. There are also public key cryptosystems. The first one, based on ordinary elliptic curves, was proposed in 2006 by Giveni, Rostovstevs, and Stolbunov. Because there's actually a sub-exponential attack on ordinary elliptic curve in isogeny-based cryptography, that is no longer used. It's also not efficient enough. And in 2011, Zhao and DeFeo came up with SIDH, supersingular isogeny Diffie-Hellman, and that's sort of one of the main ones now. And then there's also a commutative version of this, still working with supersingular elliptic curves, but only with a smaller part of the endomorphism ring. That was developed in 2018 by Kastrig, Lange, Martindale, Pani, and Rennes. So these are sort of the options, but you see that they haven't really been around for a very long time. The earliest one was developed in 2006. And so if I want to talk about, well, so what's the status of security of these systems? Well, we don't really know. So these have only been around for less than 15 years. People have looked at them. So far, they haven't really been broken, but it's also a very short time window to get some confidence if they're really secure. For example, like contrast that with RSA, which is based on factoring, and people have looked at factoring algorithms for hundreds of years, so that's a really old problem. Now, if we wanted to say something about the security or even the post-quantum security, we really need to study the objects and the hardness assumptions some more first. So there has been some progress. We can at least talk about the size of all the objects that show up in this context, isogenies, endomorphism rings, maximal orders. You can prove that they all have polynomial representation size if you pick the right description. And besides the systems that I mentioned, different ones that use different hardness assumptions, and you can sort of give reductions between the different hardness assumptions in the different systems. So to sort of understand how hard the systems are relative to each other that have been proposed. What are some of the computational challenges? Well, the supersingular elliptic curves are defined over a very small field, just fp squared. But when you have to compute torsion groups or isogenies, you have to go to field extensions, and that could result in much bigger objects, potentially exponential size. The isogenies that are used in the crypto systems have really, really large degree. So that means if you just write them down as a map, it would be too big to write down. So what you need to do is you need to, you can't write down the isogenies that are being used. You have to first decompose them into a composition of isogenies of smaller degrees and then write down those. So there are a lot of issues like this. And so what you really want to do is you want to analyze the objects through the l-isogeny graph. So here's a picture of how we might want to compute with isogenies. So there is an elliptic curve E whose points form an abelian group. And our morphism phi from E1 to E2 is an isogeny if it also it also respects the group structure. And up to isomorphism, we can just determine an isogeny by its kernel. And so what kind of questions might we have? So an easy question would be to compute all degree 2 isogenies to other curves. So there are 3 of them because there are 3 subgroups of order 2 on the elliptic curve, and the size of the kernel is the degree of phi. So if phi is a degree 2 isogeny, we need to have a subgroup of E of order 2, and there are 3 of those. That's an easy thing to compute. Hard would be if I give you a second curve E prime and I ask you to compute a 2 to the n degree isogeny between E and E prime, where n is some large number. And so that means we would have to concatenate n steps from above, from this above picture. And that's going to be much harder to do. So we do know that if I give you a curve E and a curve E prime, we do know there always exists a 2-power isogeny between them, because this 2-isogeny graph is connected, one can prove, but finding it is a totally different matter. And so if you fix the degree of the isogeny, let's say we're going to make it co-prime to the characteristic. So L and P are different primes here. Then we're going to get something that's called the l-isogeny graph, the supersingular l-isogeny graph, and we're doing it in characteristic P. So that means we're picking some small prime L, like I said, not equal to the characteristic P that we're working over. And then we have vertices and edges. The vertices are the supersingular elliptic curve up to isomorphism. So you can think about the vertices just given by the J invariants. Yeah, I didn't want to change it in my picture anymore once I had put that effort into get it to look like that. And then we'll draw an edge between E and E prime whenever there's an isogeny of degree L between E and E prime. So this is how you get the picture. Well, in characteristic P, how big is this graph? Well, it's an exponentially large graph. It has roughly P over 12 vertices, and polynomial size would be log P. And sort of what I can do in the graph is I can efficiently compute neighbors, like I mentioned before, where we did the example with L equals 2. And you can actually prove that this graph is an expander graph or a Ramanujan graph, which means it has very nice mixing properties, which we're going to use in a little bit. And finding isogenies between E and, say, in the graph E, in the find an isogeny between E and E double prime, it means that I'm looking for a path from E to E double prime in this graph. So finding isogenies of L power degree is the same thing as path finding in the l-isogeny graph. So one can use some graph theoretic tools from this as well, for this as well. Okay, I've done like a little bit background on cryptography and background on these isogeny graphs. And now I want to say something about endomorphism rings. But before I do that, are there any questions? I don't know if I can actually see it.
Yeah, I don't see any questions in the chat now, but maybe if we wait a moment and see if anyone has questions. Yes, there's one from Jeff Ashter. In the graph, do vertices correspond to geometric isomorphism classes?
In this graph, yes. If you recall that I had among the cryptosystems, the CSIDH, or C-side, how they like to call it, the commutative version, there it's not isomorphism classes over FP bar, it's isomorphism classes over FP. So it depends on what system you're working with. But the one that I'm going to discuss today, everything is over the algebraic closure. Yeah.
Okay, and he clarified just tracking J invariance or twist information. So you're normally just tracking J invariance, right? Whereas C-side would retain twist information.
Yeah. So here I'm just doing J invariance, and C-side. Yeah. So C-side is going to be different, and it's going to have a different. It's also going to have a different. Like the one is not just going to be a subgraph of the other, because of this. Yeah.
Right.
Okay, so so now I've talked about isogenies and applications to cryptography, but I haven't really said where the endomorphism rings come in. And so where do they come in? Well, computing endomorphism rings actually also has implications for isogeny-based cryptosystems and their security, because, so as I said, these recently proposed systems use supersingular elliptic curves. We're assuming it's hard to compute isogenies between them, but you can show that computing isogenies reduces to computing endomorphism rings. So there's a reduction argument there. And so what does that mean? It means if you have knowledge of the endomorphism rings of the curves involved, then you can use that to construct the isogenies. So I didn't say immediately that it's immediately going to break it, because some of these systems also ask for isogenies of a specific degree, or a degree that's of a certain size. And so that doesn't necessarily come out of this reduction. But so generally, if you can compute endomorphism rings, you can construct isogenies between any pair of supersingular elliptic curves. Okay, so far I haven't really said what's so special about the supersingular elliptic curves. Now, so here, let me say some of that. So we have an elliptic curve. It's defined over some field of characteristic P. And just to recall the definition, so before we haven't really needed it yet, so E is supersingular if the endomorphism ring is an order in a quaternion algebra. So a quaternion algebra is some 4-dimensional algebra over Q. But we can actually say even more. It's a fact that if E is supersingular, then the endomorphism ring, it's not just any order, it's a maximal order in the quaternion algebra BP infinity. And so BP infinity is a quaternion algebra over Q, which is ramified exactly at P and infinity. So it just has this form that I have on the slide. It's just abstractly just looks like Q plus Q gamma plus Q delta plus Q gamma delta. And the elements gamma and delta have squares in Q. So, and for depending on what P is, what the congruence is of P, you can explicitly, you can like write down explicitly what these look like. And so when we say that end E is a maximal order, it means that end E sits in, we can think of end E as sitting inside BP infinity is as a rank 4 submodule, and it is maximal with some property that in terms of being an order. So I don't want to go too much into the details here. We won't really need that, but sort of the object BP infinity is going to be important. So let me just keep going here. So before I say something about our new algorithm for computing endomorphism rings, I want to say what else is out there. So this really started out with, like a lot of this stuff did, with Cole's thesis in 1996, who generated a finite index subring by doing breadth first search in the isogeny graph and looking for cycles there. And the running time is O of p to the 1 plus epsilon, so that's exponential. Well, you could also, as was proposed by Galbraith, Petit, Chani, and T, just start looking for cycles in the isogeny graphs, and you could keep adding more and more cycles until they generate the whole endomorphism ring. They explain why heuristically they would expect that they would have to find log p cycles. So if you phrase it like that, then the sort of question is, well, if I can just keep generating cycles in the isogeny graph, well, how fast are these cycle algorithms? And typically, like, they're O tilde of square root p. And so here is an algorithm by Delfs and Galbraith that finds cycles by first finding a path to a curve over fp, connecting it to another curve, and then sort of going back. But so this is sort of the running time. What is our algorithm going to do? So we're also going to look for cycles, but we're only going to need 2. So, and we're going to use random walks in the isogeny graph. I already mentioned that the isogeny graph is a Ramanujan graph. And so in the picture that I've drawn, there's this green cycle in the graph that goes through the J0. J0 is the J invariant that belongs to E. And so that means it's a path from J0 to J0. So that means it corresponds to an isogeny from E to E, i.e. an endomorphism. And so there's this green endomorphism beta, and there is the black endomorphism alpha. And then I'm going to look at the subring that's generated by alpha and beta. So 1 alpha, beta, alpha, beta. And I'm going to find 2 cycles so that they generate a subring of finite index. And then I'm going to go away from the graph, and I'm going to go to the quaternion algebra side, and I'll find all maximal orders that contain the order that I found before. And I'll sort of do this locally. So that means I'm going to have some sort of local picture. So I'm going to have my order lambda tensored with CQ. It's going to be some local order. I'll find all the right guys in the local case. And then I put everything together to solve the question in the global case. And one of the orders, maximal orders that I found in step 2, is going to be the maximal order. And then I just have to figure out which one it actually is. So first, I just figure out a way, lambda, and then a finite index. Then I solve some local problem, a global problem, and then I figure out which of the maximal orders that I find is actually the endomorphism ring. Now I need a tiny bit more detail. So I actually need, so this is just a review, but like now with more all the proper conditions in, I really want the order that I find in step 1 to be one that is Bass. I'm going to say later why we want that and what it actually is. And then I have step 2 and step 3. So that's sort of how the algorithm works. So that means step 1 means we are looking for cycles in this l-isogeny graph. Any questions before I go over the cycle finding algorithm? Okay. Well, if we're going to look for cycles, we should sort of see what would you do generically if you had to look for cycles in this gigantic graph that has these nice mixing properties. So what would you do? Well, you take random walks and maybe and store the results, say. And because of this mixing property, if we take a walk of length log p, we'll end up in a roughly uniformly random vertex. And now I'm just going to repeat this a bunch of times until I find a collision. Here's so the black, the pink, and the purple path are all things that I tried in step 2. There's a blue path and a green path, and I can see that the black and the purple path give me a collision. And then I just concatenate the black path together with the reverse of the purple path, and then I get a cycle through J0. Well, the running time of this is going to be square root p log p squared. And the space requirement of this is also going to be square root p because I have to store all the different paths as I go along. Now, how might one do better? Well, you're gonna this time still take random walks, starting at some vertex J0, but this time you're gonna stop when the final vertex is adjacent to its conjugate vertex. So we have a vertex with J invariant JK, and the conjugate one is JK to the P. We're going to append this path with a conjugate pair path to get a path from J0 to J0 to the P. And what I've just talked about, steps 1 and 2, is what's given in the black right side of the graph. So we have a path from J0 to JK. I assume it has JK to the P as a neighbor, and then I go back through what I call the conjugate path, which has which is the same path, but the J invariance, I take all the P's power. And the reason why that works is that whenever J and J prime are l-isogenous, the conjugate guys are also l-isogenous, just because they're, by looking at the roots of the modular polynomial. And then the, I don't know what the color is, the orange part of the picture is when I do the same thing again to get a second path. So I can try and do that again to get a second cycle, to get a second path, excuse me. And to find the second cycle, I'll just repeat this. Now, a lot can go wrong here because these cycles might not be distinct that I'm getting, or various other things might happen, or when I compute the second cycle, it doesn't actually generate an order. But in the paper, we're able to put conditions on these cycles to ensure that we're really getting an order. So that's what's happening. So we have this picture of a path and appending it with its conjugate path. And well, if we want to analyze the running time, let me go back. Then I kind of have to figure out how often this stop condition happens. How often is a vertex adjacent to its conjugate? So that means I have to figure out how often, for how many J invariants, is J a neighbor of J to the P. And so this is a question that has come up before. And there is a paper adventures in supersingular land, of which Sarah is one of the co-authors that asked this question. And so we are answering part of the question by proving that the number of elliptic curves adjacent to their conjugates in this graph is square root p over log p under GRH. So I see there are a couple of questions. I think if I try and pull them up, it's just going to advance my document. Sarah, do you mind reading them to me?
Of course, yeah. So Rachel Priest just had a comment that it's like a collision algorithm. And Tom Petruka asks what J to the P is, the conjugate J invariant.
Oh, it's so the J invariant is going to be the 0 of a degree 2 polynomial, and the conjugate J invariant, literally J to the P, is going to be the second 0 of that polynomial. So in particular, if J is defined over, if J itself is in FP, then J equals J to the P. So, and otherwise it's literally the Pth power. Yeah, and so the collision algorithm, the first one, the naive one that I gave, you can also call birthday paradox. Yeah, are those all the questions for now?
Yes, yeah, Jeff Astor also answered the conjugate one, and then Tom says thank you for your answer.
Okay, great. All right, so this is something you need to determine. I won't really have time to talk about that today. And that theorem determines how many random walks you have to take until you find one of these, because each random walk ends in some vertex, in some uniformly random vertex. So how many of these walks do you have to take until one of them ends at one of these special vertices that's adjacent to their conjugate? We were able to prove that you need square root p log p times log p random walks. And that means that the overall running time is still exponential, because you have to take roughly square root p random walks still. But the space this time is only log p, because we don't need to store the paths. If a path is the wrong one, even if there is no later thing that could make it work, like in the collision algorithm, we never have to store the paths, so the space requirement is much better. Okay, so that was the first step. And now I just want to say a little bit of what's left in steps 2 and 3. So now we want to compute our maximal orders. And so the input is some order lambda inside the endomorphism rank. And we want to output our maximal orders containing lambda. Okay, so here's the picture again. Well, we really want to work inside some quaternion algebra that we understand. So we embed lambda tensor Q into BP infinity in this quaternion algebra. And then we're just going to determine our maximal orders inside BP infinity that contain lambda. And the way to do that is to first solve a local version of the problem. And there really are only going to be issues at the primes that divide the discriminant of lambda. So you can show that the only primes where we sort of locally have non-maximal things are primes dividing the discriminant. And then we're going to go back to the global problem and use the local information for that. So the local case that I'm going to consider looks like this. So I'm looking at like the split case here. I want to find all maximal orders containing a ZQ order. And the idea here is just to look at the Brugha-Tritz tree. And using work by Voigt, it's possible to find one maximal order that contains our given order lambda q. And then we're just going to traverse the tree and check the neighbors. So the Brugha-Tritz tree looks like this. And all the vertices in the Brugha-Tritz tree are, you can parameterize them by maximal orders. And you can compute neighbors of maximal orders efficiently. So you can compute neighbors in the tree efficiently. Now you just need one more thing to tell you that traversing the tree in some fashion and checking whether a vertex corresponds to a maximal order that contains our given order lambda q, whether this one works, you just need the following fact. Namely, if you have two vertices in the tree that contain lambda q, then all the vertices in the path between O and O prime also contain lambda q. So that means it really just comes down to traversing like a subpiece of the tree. Well, and the efficiency of the algorithm really only depends on how many of these lambda q's there actually are. So we're trying to find all lambda, how many maximal orders there are that contain lambda q. There could be really a lot, or there could just be one. This is where this notion of Bass order comes in that I said before. So I'm defining it here. But really the fact that I need is what I just put up on the slide, namely that when lambda is Bass, I can bound how many maximal orders there are in the local case that contain lambda q. So that means when lambda is Bass, this whole algorithm is going to be efficient. And that's the main reason that we want the condition there. And then I just put the local information together to get the global answer. So now we want to go away from the local case and go to BP infinity. And we're just going to sort of enlarge our order lambda 1q at one prime at a time. And so we can sort of compute these orders that I have written down in step 1 here that are maximal everywhere except at q. And at q they agree, sorry, the other way around. The order that are maximal at q and everywhere else they agree with our original order lambda when we tensor with zq prime. We can compute those from the local information that we just did in the previous step. And then we sort of take sums of the orders that we found in step 1, and that gives us a maximal order that contains lambda. And if I take all possible sums, I get all possible ones. So that at this point, it's pretty straightforward to put things together. And so since I have, I'm almost out of time, let me just move on to the third step. So now we're in the situation where we have all the maximal orders and we just want to figure out which ones of the ones is actually the endomorphism ring. And so what does that mean? So that means I really have to try them. Like I take a maximal order O that I found in step 2. And I have a supersingular elliptic curve, and I need to solve the problem of deciding whether O is the endomorphism ring of E. And well, the way to do this is it's basically already been solved, because you can actually construct a curve whose endomorphism ring is O. I'm going to call that E prime. And well, now you just check whether the curve you constructed is isomorphic to the one you were given, or if they may be off by a power of p, because a curve and its conjugate have the same endomorphism ring. But because those are the only two options, those are the only two checks you have to do. So you first compute this curve E prime that can be done efficiently under some heuristics, and then you compare J invariants and see if they're either the same or off by a piece power. And like I said, the fact that I'm using here is that the endomorphism rings are the same if and only if, isomorphic if and only if the J invariant of the first is equal to the J invariant of the second raised to the pth power. So that means the association E goes to its endomorphism ring is either 2-to-1 or 1-to-1, depending on whether the J invariant is in FP. So if the J invariant of my curve E is already in FP, then up to isomorphism, it's the only elliptic curve with endomorphism ring O. And if it's in FP squared, then there is another elliptic curve out there, namely the one with J invariant J of E raised to the pth power. Yep, and so the running time of the whole algorithm is still square root P log P squared. There are some heuristics needed because we need to make sure that the cycles that we have generate a Bass order. We did some experiments that show that this happens usually after a few attempts. So that does not seem to be a big obstacle. But we also need to bound the number of global orders containing lambda when the discriminant is not square free, which also does not seem a big deal. We can verify that in experiments. And the bottleneck seems to be the cycle finding algorithm, which I presented in the beginning. So the cycle finding algorithm has the same complexity as the overall algorithm. So that is the bottleneck. It saves a factor of log P compared to previous approaches to compute the previous approach to compute the endomorphism ring, because we really only need the cycle finding oracle constant number of times. And that means, so that's sort of the running time. And now let me just summarize my talk. So I gave you an algorithm for computing endomorphism rings of supersingular elliptic curves that uses a first part, a cycle finding algorithm, and then works in local and global quaternion algebras. The running time is O of square root P log P squared. And some obvious questions are, is it possible to remove the heuristic assumptions that we have to make? And for this bottleneck that I mentioned, is there a polynomial time algorithm that finds cycles and graphs? That would be very interesting also for other applications of for isogenies. And so I think with those two questions, I'm going to stop, and thank you.
Okay, thank you very much, Dr. Eisentraeger. We will all clap and thank you virtually. I'm sure everyone is clapping where they are right now. And in the chat, people are clapping. Let's see. There was one question from earlier about what the Bruhat-Titz tree is. Could you say a little about that?
Yeah, so you mean the definition of the Bruhat-Titz tree?
Yes, yeah.
So the Bruhat-Titz tree, the vertices in the Bruhat-Titz tree are the, let me just pull up the vertices in the Bruhat-Titz tree are the maximal orders in M2QQ. And to each of these maximal orders, you can also associate a lattice. And then two vertices are neighbors if the corresponding lattices, if you can multiply one by like a number and map it into the other. So it's a containment between lattices after some map. So this is the thing you can check. It's just gonna, yeah.
Okay, thank you. Yes, and then Yana Sotakova asks, how large were the experiments that you tried to get the Bass orders?
Yeah, let me look that up. Let me look in our It's a good question. So we tried like p's up to 100,000, and then sort of try to see what percentage was Bass. And so for like p's up to 100,000, the percentage was like 70% of the orders that we generated were Bass.
Okay, and do you expect that trend to continue for larger P, or was it changing with the size of the prime, like the percentage?
No, it actually got better.
Oh,
but I mean, it's not really, I mean, 100,000 is of course still far away from being of cryptographic size, so it's can't really tell what would happen when the prime gets that much bigger. Yeah.
And then one further question, is it possible to put conditions on the cycles that generate lambda so that the number of local maximal orders containing lambda sub p is small?
Yeah, that's exactly the Bass condition that makes that work. Okay. So if you have this condition that satisfied that lambda is Bass, which I had on the slide, then you can get an upper bound on the number of maximal orders that show up locally. Yep.
Can you see that from just the cycles though, or you have to, or I guess generating lambda isn't that hard once you have the cycles, so it makes sense.
What do you mean?
Sorry, I talked myself out of that whole.
Well, it's just that, whether or not an order is Bass is something you can check efficiently. So it's just like you have to compute the order that the cycles alpha and beta generate, and then see, you can check it with some discriminant condition and trace condition, and just, yeah.
Yeah. Okay. All of the people that ask questions, thank you for your answers as well.
Yeah, I see that now.
Yeah.
Yeah.
Okay, got it. Good. I was wondering, I guess, if you could say a little something more about step 2, just when you're in the global picture, sort of picking between the possible maximal orders. How did that part work?
You mean when you already have all the maximal orders and then picking the right one, or before that?
Right. Yeah, picking the right one.
Yeah, so basically you have to check them all. So what would be is, so your list of you have your list of global maximal orders that are candidates. Let's say they're called O1 through ON. And if you want to know, for example, if O1 is the right guy, you take O1, and this algorithm that I was referencing allows you to construct an elliptic curve whose endomorphism ring is isomorphic to O1. And so now you know an elliptic curve, and now you can just check, is that elliptic curve that you just constructed, does it have the same J invariant as the one that you were given? Or are they just off by p-th powers? And if either one of those is true, then O1 is your guy. And if it just has a completely different J invariant, then you know not your guy. And then you have to move on to O2. So that means if you have exponentially many orders that come out of this whole construction, starting with lambda, if you get exponentially many that contain lambda, then you're kind of lost right from the get-go, because then you can't be polynomial time anymore. So for example, if lambda were to be the intersection of all maximal orders that exist in the graph, then there would be no hope that this could be polytime. That's why you sort of try and get a good lambda to begin with, so that this doesn't blow up so much. Yeah.
Yeah. And then Catalina Camacho asks, can you describe the heuristic assumptions again?
Yeah. So the heuristic assumptions are that one of the heuristic assumptions based on our calculations is that we only have to run the cycle finding algorithm, like finding pairs of cycles, only a constant number of times until the order is Bass. And so from the experiments, we sort of got that 60 to 70% of the orders were Bass. So that seemed pretty reasonable. And so that's the first heuristic. And then also, we can prove everything unconditionally if the discriminant of the order that we're getting is square free. But if it has square, if it's not square free, then we have to make another assumption that we're still getting only polynomially many orders, super orders. So that's another assumption we have to make. But that one, it might be possible to just get rid of that second assumption with just better analytic number theory methods. And then there's GRH, because we needed a class group estimate to bound the set that you're familiar with, Sarah, the one with the J invariants that are neighbors to the conjugate.